All right, folks, this is, actually, I think it's 7.4 is what, it's part 2, the check for understanding for the shooting guard lesson. And here's the 2 main takeaways here up on the top. Even if you have a distribution like the shooting guard distribution, the shooting guard distribution was kind of skewed left like this for all the shooting guards in the NBA. Even if this is the case, you can still model it with the normal distribution as long as your sample is large enough. Because remember, a good sampling distribution, the most important thing about it is that the mean of the sampling distribution matches the mean of the population distribution. So even though this is skew, if you take enough samples, your samples are zeroing in on the mean. These skew data points will maybe occur here and there, but the majority of them will be here on the mean, so it will be a symmetric result. Anyway, all right, so here's the question. The company has a contract that performs preventative maintenance on air conditioning units. Based on service records from the past year, the time and hours that a technician requires to complete the work follows a strongly right skewed distribution with an average or a center of 1 hour, a mu of 1 hour, and a standard deviation of 1.5 hours. As a promotion, the company will provide service to a random sample of 70 air conditioning units free of charge. You plan to budget an average of 1.1 hours per unit. Keep that in mind. And will that be enough time? All right, so before we answer that, let's do number 1. What is the shape, the center, and the variability of the sampling distribution of X bar for the sample size of 70 from the population? So the shape is approximately normal because of the central limit theorem, which is right up here. As long as your sample size is greater than or equal to 30, which it is because it's 70, you can confidently say that it is approximately normal. Even though they didn't say the population was approximately normal anywhere up here, you don't have a plot of it. It doesn't matter as long as the central limit theorem is satisfied. The center of the distribution will always be the population mean of an hour. Now the variability is not just 1.5 hours. Remember that 1.5 hours would be for, this is for 1 service call, okay? But we had 70 service calls, so remember in the standard deviation, you need to divide by the square root of 70 because that's the sample size. So your standard deviation of your sampling distribution is 0.179 hours. Okay, number 2. What is the probability that the average maintenance time for 70 randomly selected units exceeds 1.1 hours? Because remember up here, that's what they budgeted. It says they plan to budget an average of 1.1 hours per unit, and they had 70 units. So in other words, for this sample of 70, what's the likelihood that the average is higher than 1.1? So here's the distribution. We just found the information up here. 1 hour is the center, right? And they're counting up and down every line by, you can't see blue on blue, can you? By 0.179 and then plus 0.179 plus 0.179. So just sketching this right here is super helpful. I can tell right away just by sketching it that it's a decent probability, you know. Without even looking at it, I'd say this is, 25, 30, 35% or something like that. So we need to find the z-score. So we take our 1.1 minus the average. We're using this formula right here. We take our sample average, which is 1.1, and subtracting the population average, which is 1 hour, and dividing by the standard deviation that we found. So that is all right here. So this z-score, I'll write it above, is 0.56. That is going to be my lower. If I'm going to do normal CDF, that's my lower, okay, 0.56. And then my upper is just way off the end. It's going to be 99. And then 0 and 1 if your calculator asks you for those two data points. And you will get that, or you'll get something quite close to it. If you use your table A, your green packet in table A, remember it will give you the orange side. The orange side is 56%, no, sorry. The orange side is 71%. Okay. You just have to always remember to do 1 minus that, like they did right here, 1 minus 0.7123. So what that means, you guys, is this. There is about a, 29% probability that the average maintenance time for all 70 maintenance calls will be more than 1.1 hours. So now we can finally answer the question. Did they budget enough time? No. I mean, based on your answer, did the company budget enough time? No. According to the distribution and number 2's answer, 29% of the time, well, there's a 29% probability that they did not plan enough time. They did not allot enough time because they only planned for right here for 1.1 hour. So anything past here, they don't have time for it. They didn't budget for that. And this is way too big. The only 5%, less than 5% would be acceptable. Okay, that's kind of the cutoff that we have been using. So in other words, if hypothetically I had done this whole calculation and this number turned out to be like 0.03 or something like that, well, that's less than 5%. So then I would say, well, sure, well, then they budgeted enough, because according to that answer, if it was 3%, they would only have not budgeted enough in 3% of the situations that could arise, and that's a risk they're willing to take. All right, see you later.